So let's continue. So we just had the brief introduction to what we will study this semester, and also a very important statement that everything in solid state physics is about Green's function. So this is a very important key concept that everyone should remember. So today we will formally introduce mathematical definitions of Green's functions. But before we provide this formal definition of Green's functions, this Green's function and as a mathematical technique has been widely used even in classical electrodynamics. So in classical mechanics and classical electrodynamics, you already learned Green's function, but you didn't know that those functions are called Green's function, and those techniques are called Green's function techniques. You have known this, you have studied this, but you didn't realize this. And let's just go back a little bit to the classical electrodynamics and refresh your memory about this, and then we move to the quantum mechanics version of the Green's function, and then you will see that this concept and technique that lead to the Green's function formulations are really similar between classical and quantum mechanics. So let's just look at this classical Green's function approach. In the problem that you already solved, this so-called Poisson equation for electric potential phi, that is the function that you need to know because of this charge distribution, density rho E of r distributed in space. And this is a famous Poisson equation that you need to solve. The Laplacian phi of r is given by the right-hand side of this equation, minus 1 over epsilon 0 times this electron density. So you know the solution very well, but now we would like to solve the same problem using Green's function technique. So instead of directly solving for this equation by a Fourier transformation, so let's just solve a much simpler equation. Namely, we solve this equation, Laplacian acting on this so-called Green's function, capital G as function of space R, and on the right-hand side of the equation is just simply just a Dirac delta function, delta R. And we forget about this charge, but we just pretend that we solve this G of R, which we call this Green's function, which is much simpler to be solved. And then later, the full solution of this electric potential phi will be a function of the capital G of R. So that's the Green's function technique. Maybe some of you already learned this in your electrodynamics, but let's just repeat. So suppose we know the solution of capital G of R, then we will show that the full solution of electric static potential is given by an integral, so convolutional integral. And inside the integration, we have the electron density function, rho E of r prime, but not just this electron density, but we need to sum over all contributions to the electrostatic potential, and by multiplying a factor called Green's function, which is a function of distance between these two locations. One is the charge distributed place, and then another is the point that you want to know the potential. And the Green's function depends only on the relative difference between these two special coordinates, r and r prime, and then you perform this convolutional integration by multiplying these two functions together and integrate over your entire space, r prime, and then you get to this electrostatic potential 5r. So instead of Fourier transforming this full Poisson equation and this Green's function, although it's rather indirect, but it is more informative that you will benefit from this kind of indirect solutions by means of this Green's function. So you could go back to your textbook on electrodynamics. So let's just very briefly show that they are equivalent. So let's perform the Fourier transformations on this Green's, the equation for capital G of R, which means that this is minus k squared, G is function of k, which is 1. Remember this delta function, if you Fourier transform this after normalization factor, this should be 1. Remember that. And the Fourier transform of this Green's function G of R in k space is given by this function G as function of k, and this Laplacian, this gradient square, when you perform the Fourier transformation, it leads to k squared, because this is second derivative of this Fourier phase vector, right? Gradient square e to the I k dot r, something like that. So you know this very well. And because you take the second derivatives, there's a I squared in front, and that's why you get this minus 1. And so you immediately know the solution of g of k, because this is simply just 1 over k squared by this simple Fourier transform. And this g of r could be obtained by an inverse Fourier transform, and you know very well what it leads to. So if you really integrate out this vector in this three-dimensional k space, what you get is just a number, minus 1 over 4 pi times r, whereas r here, it is the coordinate in real space, but it is independent vector of this k space variable k. So this is the solution, almost solution. So you know this spatial dependence of this Green's function, g of r, you know what it behaves, and by this second statement here, that the full solution of electrostatic potential is given by this convolutional integral, and this is the integral that you need to do and to get this solution. Okay, so this phi of r using this Green's function method is given by this, and if you study electrostatic theory, and you immediately recognize that this is the correct solution for Poisson equation, right? Okay, no question, no problem, right? It's straightforward mathematical, a little bit manipulation, but while at the end you get the correct answer. But let's just put this as a little bit of homework problem. So there is a homework problem. Suppose that this is the correct solution for electrostatic potential of Poisson equation, and you want to prove that. Okay, so suppose you plug in this assumption here back to the Poisson equation, and in order to satisfy this both equations, Poisson equation and solution for electric potential, and you need to satisfy the equation for the Green's function and prove this or derive it. So this is an acute exercise for your review, that this kind of ansatz or a guess is actually an educated guess, and it is consistent with all these equations here. So you want to show that all these equations are really consistent. So it doesn't matter where you come from. If you come from this equation, you get this and that. If you come from this, you get this and that, and so on and so forth. So all the three equations are really consistent. And by doing so, you are convinced that this Green's function method is actually the equivalent way to find the correct solutions for Poisson equation.
Right. This solution only for the you already fixed the boundary condition, right?
Of course, this is just the simplest possible example in electrodynamics, that you have a static charge distribution, rho E of r, and you want a solution for Poisson equation. And you can solve this equation two ways. First is by brute force Laplace transformations on both sides of the Poisson equation. The second one is the smarter way, which is the Green's function method. And this is the first time that people introduced the Green's function mathematically in order to see this relation between the electrostatic potential and charge distribution density. And in some way, this Green's function links between this potential and the charge density. Okay, so the Green's function in every way is the bridge connecting two things. In quantum mechanics, it connects two quantum states, or two operators at different space and time, and momentum or frequency anyway. So let's just, with such a worn-up exercise, we can formally introduce the quantum mechanical version of a Green's function for a very simple example, which is the one-particle Schrödinger equation. So everyone should know this, should have known this already. It's just that you didn't realize that you can solve the Schrödinger equation, the time evolution of Schrödinger wave functions, by using Green's function approach. And very similar to this classical electrodynamics, we can solve the Schrödinger equation by using Green's function approach. So let's just look at this very simple Schrödinger equation, time-independent version. It is an eigenvalue equation. So again, we could solve this single particle Schrödinger equation, time-independent version, directly from our quantum mechanics knowledge. But here, we will solve it in a different way, namely by using Green's function approach. So by the same token that we solve the Poisson equation here, we do not solve this psi of E directly. Instead, we first solve the Green's function for this corresponding Schrödinger equations. And then the full solutions will come up when we have a similar convolutional integral like this could be derived. Okay, so this is the logic. We don't solve this equation directly. Instead, we solve the much simpler version of that equation. On the right-hand side of the Schrödinger equation, it is simply just a Dirac delta function. So the corresponding Green's functions equation for this time-independent Schrödinger equation is given by this E, right? We consider a very simple equation like this. So on the left-hand side of the equation, it is simply just E minus H0, when H0 is just a non-interacting part of the Hamiltonian. And you know this eigenfunction of H0, but this G0 is just a non-interacting version of the Green's function, okay, where you consider the absence of V in your Hamiltonian, and then you solve for this non-interacting part of this Schrödinger equation by solving this corresponding Green's function called G0. This subscript 0 refers to the fact that this is, this Green's function for H0. So then you could invert this relation like this. Okay, so you can show that this inverse relation of this non-interacting version of this Green's function is given by this one. Okay, so you could use your knowledge in quantum mechanics. So then eventually what you want to show is the Schrödinger equation for this interacting version of the Hamiltonian is given by the solution of this equation. And the solution for this equation is a very similar convolutional formula for this eigenstate in the presence of the interaction V. So which means that if you want to know this eigenfunction in the Schrödinger equation for this interacting system, then what you need to do is to solve first the non-interacting version of the Green's function G0 by solving this equation here or here. And then when you get this G0, and you simply just plug in this G0 here inside this convolutional integral, and then this will be the correction to the unperturbed part of your eigenfunction. Your full solution, which satisfies the Schrödinger time-independent Schrödinger equation for an interacting system, is given by the non-interacting part of the eigenfunction plus this convolutional integral. Right. This is, if this is 0, and this will not be 0. So this is kind of a iterative equation. So the solution psi of E of R depends on the right-hand side of this convolutional integral. Okay, so we will come back to this later. So you could use the same logic to find this eigenfunction for interacting problem of Schrödinger equation by solving this non-interacting version of the Green's function. But so we will come back to this non-interacting version of the Green's function later, but this is just a sketch to show to you that by following the same logic that you solve the Poisson equation by Green's function, you can also solve the Schrödinger equation following this Green's function approach. So let's take a short break. When we come back, we will move on to the time-dependent version of the Schrödinger equation. But anyway, we will come back to this kind of an iterative equation later. So for those of you who are taking this course, this is another homework. Prove it. Prove that this is indeed the solution of this time-independent Schrödinger equation for the interacting system. So remember, this G0 minus is given by E minus H0. So if you plug in this G0 inverse here, and this is precisely your original Schrödinger equation. So if you plug in this E minus H0 minus V, which is the same equations if you move the left-hand side of equation to the right. So this is the same equation as this one. In other words, to solve the equation 1, you could use the equation 2 to solve the equation 1, but you know how to solve the equation 2 because you know G0, and therefore by solving the equation 2, you solve the equation 1. Get this? Okay? It's an indirect way, but it's a very powerful and useful way. So let's take a short break. So by the way, the stuff here, those equations and those Green's function approach can be found in our textbooks, chapter 8 about Green's function by Flansburgh. So you could go back to check your textbook. Okay, so please ask questions if you have any time. So let's look at the same approach to solve these time-dependent Schrödinger equations. So we know very well from quantum mechanics that you have this time-dependent version of the Schrödinger equation in the presence of interactions V, and you want to know the eigenfunction or Schrödinger wave functions of this time-dependent version. Okay, so of course the solution will be very complicated. So precisely because of this Green's function approach is really powerful and useful, especially for those very complicated Schrödinger equations or other many-body equations that you want to solve. So when you really want to solve these complicated equations like this, and V of R could be very complicated function. So you really don't have a good way to solve this, unlike this Poisson equation or time-independent version of the Schrödinger equation. So you have nothing, you have no weapon. So the Green's function method is the only weapon that you have. Okay, so now you see the power of the Green's function approach. So again, so we do not solve this time-dependent Schrödinger equation directly. Instead, we solve the equation for the Green's function first, and then full solution will be a function of Green's function. So the corresponding Green's function are the following. So you tend to solve this G0, the non-interacting version, first, and then you try to solve the full Green's function later. So on the right-hand side of the equation, you get two delta functions. One is the spatial delta functions, depending on the relative distance between these two spatial locations on R prime, and you get another delta functions in time, which tells you this time difference between these two quantum particles. And you also have this interacting version of the Green's functions, which is just a capital G without this 0 in the subscript. This G without the 0 refers to the full Green's function, which is a Green's function for the full Hamiltonian. And G0 is so-called a bare Green's function, and that is just for H0. So G0 is much easier to get than the full Green's function G, because of course, if you don't have the interactions, everything is very simple. So let's try to solve these two equations for the Green's functions. And so let's just invert that Green's function equations. So G0 inverse and G inverse. So regarding to the inverse of these equations, you could check your quantum mechanics for details. So eventually this is actually operator H0, and you could apply this eigenfunction on both sides of this invert relations, and you can show that you can satisfy this G0 equations, and similarly for this interacting version. And we have not solved this G0 yet, but we just sketch how we get the full solutions of a time-dependent Schrödinger equations based on what we find for this G0 and G. So suppose we know G0 or G. The solution is simply this kind of a convolutional integral equation. Or if we solve the full Green's function by solving the second equation here, then we can still get the same solution, but in a slightly different expression. Both expressions are equivalent. And this is precisely what the earlier questions was about. And these two equations are really equivalent, meaning you either can solve this to get the solution psi by solving the top equation number 1. Remember, in this top equation, this Green's function has a subscript 0, which means that this is a bare Green's function for the non-interacting version. But on the right-hand side of this integral, this psi is actually the same psi right here, which is the same interacting version of your eigenfunction. So this is the full solution, and this is also your full solution. As a result, this is not yet solved because the psi of RT is what you want to know, which is unknown. On the right-hand side, this psi is also a full Green's function, which is also unknown. So both psi's on both sides of the equations are completely the same. But of course, this position and this time for these two psi's are different. So in order to get this full solution, you need to really go back and forth, do things like Dyson equation or perturbation theory, that you could iteratively solve these integral equations simultaneously on both sides. Suppose that everyone study quantum mechanics should know the perturbation theory or spirit of the perturbation theory. So this psi 0 plus this complicated object. So first you plug in this zeroth order solution, which is psi 0 right here on the right hand side of the integral, and then you know everything because you know G0, you know psi 0, you can do this convolutional integral, and then you add this psi 0 here, and you get the first order corrections to psi, which is psi 1. But this is not yet done because this is just your first order corrections on the right hand side, right? So you should continue. So this is, which I think this is just psi 1, and of course you need to add the contributions from the second term here on the right hand side. The second term right here depends also on psi, but you can make a simple approximation by using simply the psi 0 to approximate this psi 1 integral, and you also get the second order corrections, which is second order in V and also in psi 0, and so on and so forth. So you get infinite number of terms. And of course, you get psi 1, psi 2, and so on until psi infinity, and at n iterations. So you may find that the left-hand side of the equation is more or less the same as the right-hand side of the equation, and that's the iteration when you get a convergence. When you get a convergence on both sides of the equation, you can safely say that I found the solution. Until then, you should do this iteration back and forth many times until your solutions are convergent. So this is the first way that you find this full solution for the time-dependent Schrödinger equation. But the second way is the opposite approach or orthogonal approach to the first one, because now you see this G is actually full Green's function, right? If this G is full, then this psi should be psi 0, which is the eigenfunction for the bare Hamiltonian H0. And so what is G, right? So you should solve the G by solving this equation here. G is actually a function of G0 plus G0V G0 and so on and so forth. So I'm going to derive such a infinite series in just a moment, but let me just sketch what procedure is. Procedure is that you find full solution G in the form of this infinite series here, and then you plug into the integral, but you know this psi 0, you know the V, and you perform this convolutional integral, and you get the final solution. So there is only one 0 here. Either you put it in G or you put it in psi, and there's only one non-zero here. Either you put it in psi or you put it full Green's function G. So you do not have 0, 0 here or non-zero over here. So this is equivalent way, because whether you would like to sum over all these interaction effects within the framework of the Green's function or within the framework of the psi is your choice. It doesn't matter. But you cannot double count this effect of interaction, because interaction can only be counted once. Either you put all the interaction effects in the Green's function or in this psi. But you cannot put interaction effects on both functions, G and psi, or you simply just use two zeros. If this is just two zeros, you simply just get the second order bare perturbation results. So let's just do the iteration. So as I mentioned, if you perform this iteration, you will see that if I perform this iteration for this first equation, so I'll get psi 0 plus G0 V psi 0, 0, v 0, v 0, dot dot dot. So you could very easily get this full Green's function from this geometric series. Okay, so now you see the equivalence between these two approaches and two integral equations. So I come from this first equation and I do iteration, and when I do so, I find infinite number of terms in my series. Of course, I neglect all these double integrals, which is troublesome, but you could rearrange all these terms, right? Okay, I could rearrange anything I like. Okay, so what I want to reorganize is this kind of organization here. So I put all this v psi 0 as a common factor on the right hand side of the bracket, but inside the bracket I get g0 plus this plus second order and plus all the way to infinity. But I can recognize what is this. This is nothing but the full Green's function. Okay, but what is this? Well, this is certainly the thing that's written for the second line right here. So this is the second equation. So this is the proof that either way I can get the correct full solution of time-dependent Schrödinger equation by using Green's function approach. So the benefit of this is to really establish this so-called Dyson equation. So G, as I mentioned, is an infinite number of terms in order of V interaction. So and this is so-called Dyson equation. It means that this G is actually G0 plus G0V times G, because this is also G. If you look at this term inside the bracket, I can organize all this term, infinite number of terms inside the G4 bracket. And what I get is this organization here. So, but if you look at this both sides of the equation, you get the G4 is given by G0 plus all this infinite number of terms. But if you look at this bracket, I mark yellow here, and this is precisely the full Green's function. So the full Green's function on the left-hand side is a function of the full Green's function on the right-hand side. This is a unsolved equation, and this is a famous Dyson's equation. So symbolically, mathematically, this is a full Green's function, which is yet to be known, and you don't know this. But this is given by this integral equation on the right-hand side. So again, you need to go back and forth to get this perturbative expansions of this G in terms of G0 and V, and order by order. And after many, many iterations, you could get the convergence between two sides of the Dyson equation. When you get the convergence, you find this G4. When you find the G4, you plug in here, and you get the solution. So the corresponding solutions in the Schrödinger formulation is this. Psi r of t is given by dr prime g r t r prime prime m psi r prime t prime. So this is the solutions of this time-dependent Schrödinger equations. If you really want to use this simple integral equation, just one term. And that one term, you get full Green's function here, and also full solutions on the right. So again, so if you simply just expand this psi or g in terms of g0 or psi 0, either way, you get either first equation, the second equation here. So they should be fully equivalent. And so this is so-called the Green's function approach to Schrödinger equations that you may have known this in quantum mechanics, but you may not notice this approach. So this clearly tells us that the Green's function actually links between these two Schrödinger wave functions at different space and time location, r, t, and r prime, t prime. And if you know all this previous history of this your Schrödinger wave functions, and you perform this convolutional integral, and you know the present time or psi at any specific location, space-time coordinate r and t. So your wave function for a quantum particle at particular r and t could be obtained or derived from all these wave functions at different space-time coordinates subject to such a Green's function convolutional integral. Therefore, the Green's function is sometimes called the propagator because it tells you how this quantum particle propagates from one spatial time coordinate to another, and how to link this same quantum particle states at different space and time locations, because this wave function not only time evolves but also evolve in space. So how this quantum particle state evolves in time and space could be described by the Green's function. As a result, the Green's function is really the key to all this many-body physics, because it tells us how you could correctly get the solutions. If you know, how they are correlated at different space and time, and you know everything. So everything that you need to know is hidden in the Green's functions. Okay, so later we will define a single particle Green's function for free fermions and for free bosons, and then we will try to evaluate G0 and also G4, and later, some later stage, we can come back to this Dyson type equation to solve the Schrödinger equation. Okay, so let's take a short break. When we come back, let's just continue to define more formally the Green's function in terms of the propagator of a quantum particle state. Okay, so let's continue. As I mentioned, the Green's function can be interpreted as the propagator of a quantum particle state, and you can see this correspondence in this equation here. As I mentioned, the full solutions of this time-dependent Schrödinger equation could be expressed in terms of this convolutional integral, and the Green's function is actually the bridge between these two Schrödinger wave functions at different space and time location. So this is the connection or link, and therefore it is the propagator, which tells you how this quantum particle propagates in space and time. In other words, this could be viewed as in quantum mechanics, the transition amplitude of a quantum particle that moves from one space-time to another space-time location. What is the transition amplitude? So the square of the transition amplitude is the transition probability, right? So what we are trying to calculate is the transition amplitude between these two quantum states. It's a space and time evolution of a quantum mechanical states. And then we could use this interpretation to define various types of Green's functions, which I will define in the following. The first two sets are called the retarded and advanced component of the Green's function, which has this definition right here. For the retarded, I put this capital R on top of this capital G here, and then on the right-hand side is the formal definition of this retarded Green's function, and there is a theta function, and you know how this theta function behaves, right? It's 1 if x is positive and 0 if x is negative. So the right-hand side of this definition of the retarded Green's function vanishes if t is less than t prime. So if t is greater than t prime, and the theta function gives you 1, which has a finite contribution, but if vice versa, t is less than t prime, you get 0. So as a result, this tells you the relation between these two wave functions. One comes earlier than the other, or later than the other. So t prime is an earlier time, and t is a later time. And another corresponding Green's function is called advanced Green's function, which has the opposite definition compared to the retarded counterpart. There's a theta function right here. By the way, there's a minus sign here in the retarded Green's function, but there's a plus sign, plus I theta, but in the theta function, the argument is really opposite. It's t prime minus t, which means that you collect only when t prime is larger than t. So we will describe why we need this retarded advanced components of Green's function later, but let's just live with this definition, because many physical observables can be more conveniently expressed in either retarded or advanced version of the Green's function. And this is the matrix element between r and r prime spatial locations, and with e to the minus ih Hamiltonian operator times t minus t prime. So this is a matrix element. And inside the matrix element, this is the operator, H wearing a hat, which means that this is a quantum mechanical operator. So this is exponential operator acting sandwich in between position eigenbases R and R prime. And this is highly non-trivial because this H consists of non-interacting H0 plus the potential term. Remember that. And you don't know the full eigenfunctions of this full Hamiltonian H. So you don't know the final answer if you really calculate this sandwich, this expression value, or this matrix element. We could just define this retardant advance Green's function as a matrix element between the two spatial locations of the exponential I Hamiltonian operator times the time difference and multiplied by the theta function. So here's your job. You can show that if I define this retardant advance Green's function like this, and these two definitions satisfy the equation for full Green's function that we just talked about a few minutes ago. Meaning, if you plug in the definition of this matrix element times theta function, and you can show that you can satisfy this equation. So the homework for you is to show that they are indeed the solution of this full Green's function. Even though I don't know the solution, they simply satisfy this equation for Green's function, for full Green's function. And if I define this Green function like this, and it is very easy to interpret in terms of physics because this is nothing but this evolution, right? Spatial evolution of your Hamiltonian operator, e to the IH, between these two spatial locations. So let's just really interpret this GR and GA, the advanced and retarded component, retarded and advanced component of the Green's function. So as I mentioned, this GR or GA could be understood in terms of the probability amplitude of a quantum particle in state R at a later time t, while it was at state R prime at an earlier time t prime. So this is what I meant by retarded, because retarded means that you actually measure what you want to know about this wave function is at the later time. It is actually retarded. Means that what your interest is the wave function at time t, which is a later time than this earlier time t prime. So if you use the plot, and this is your retarded Green's function. Suppose t prime happens at the earlier time and t is a later time. So what you calculate here is the transition amplitude or probability amplitude of the quantum particle state evolving from earlier time t prime to the later time t. And likewise, you know the meaning of G advance, right? It's the opposite definition, which means that you want to know this transition amplitude of a quantum state that happens at the earlier time where you know this wave function at the later time. Okay, so you know the corresponding definition for G advance, so I will not repeat. And you could actually use different bases, eigenbases, to expand those matrix elements. Okay, so any complete set of eigenbases are fine. Suppose you know some eigenbases, for example, the position eigenbases, the momentum eigenbases, whatever eigenbases you know, and you could expand this matrix element, this sandwich between R and R prime, this kind of matrix element, in any complete set of eigenbases you like, such as phi n here is a complete set of eigenbases. You could use your quantum mechanics to really expand this matrix element in any kind of complete set of eigenbases you like. And if you do so, then you immediately get this number here, which is not the operator anymore because you already operate this kind of a matrix element calculation. So when you know eigenbases of your Hamiltonian, and you can really calculate this eigenenergy and express this capital En in your exponential factor, and after you perform such eigenbasis expansion, I guess that's about this physics interpretation of a single particle Green's function. So let me just stop here for a few seconds for your questions. So next we will go to the more mathematical definition of various single particle and many particle Green's function, and then perform the Fourier transformations to get various forms of Green's functions in space and time, also in momentum and frequency basis. And in many experiments, what you really measured is the spectral density of your Green's function, which is the imaginary part of your Green's function G in momentum and frequency basis. And this is something measurable, and we should be able to calculate those measurable quantities within the Green's function formulation. Okay, so far it's simply just a mathematical formulation and the physical interpretation. But I think this is really a good exercise, because this interpretation of the retarded advanced Green's function comes directly from this definition. But this is not just a definition. This also satisfies this equation for full Green's function. As a result, this definition should be considered as a solution. It's a kind of a semi-solution. Even though I don't know this eigenstate for this full Hamiltonian, but mathematically, if I am able to calculate this and I know everything, and this has the perfect interpretation of a transition amplitude like this. So the mathematics and physics actually come side by side. They coincide. It's not just a mathematical equation, but it has the physical consequence and physical interpretation. And that physical interpretation comes from this rigorous mathematical formulation of the Green's function. So there's, yes?
我想问一下，那个 Foley 的 Green's function 就是 retarded 加上 advanced 吗？还是其实不是这样的想法？
We will define the relation between the full Green's function and retarded advance. So thank you for your question. So that's the thing that we will talk about just now.
好，我第二个问题就是那个很像费曼图的那个线，那我可以把它想象成就是在 R' 跟 T' 那个地方生成一颗粒子，然后在 R 在 T 的地方消灭一颗粒子。
Precisely. We will define this in second quantized fields. That's precisely what you mean, okay? And you understand correctly, okay? So here we consider that we sort of destroy, say, electron here at R', T', and we create another electron, another place and time. And we calculate this transition amplitudes of such a particle-Hall pair, excitation or whatever, evolution. Any other questions? No? Okay, good. So let's just move on. Let's go from the easiest part, which is a zero temperature Green's function in a many-body system. Okay, so again, you could look at the Flansburgh chapter 8 and also the other textbooks. And to do so, you need to define your quantum mechanical operator in the Heisenberg picture. So you know very well the Schrödinger picture, Heisenberg picture, and interaction picture, right, in quantum mechanics. And here, we like to follow the Heisenberg representation of a quantum mechanical operator, meaning this Heisenberg operator evolves in time, but the state fixed. In Schrödinger picture, it's the state that time evolved, but the operator stays stationary in time. But either way is fine. But this kind of Green's function formulation is more conveniently expressed in terms of the Heisenberg operator. So let me just give a very brief review of a Heisenberg operator. Heisenberg operator is an operator defined in such a way that you perform a unitary transformation on the Schrödinger operator. This psi s refers to some Schrödinger operator, and psi h is the Heisenberg operator, and it is a time-evolved Schrödinger operator like this. And we could define our single particle Green's function in the many-body background. So this is highly non-trivial because even though this is a single particle Green's function, but you know that there are many, many single particles in your system. So even though you simply just look at one particular electrons, but that electron interacts with all the other electrons. So this is highly complicated function, and but we can formally define this G alpha beta for a single particle out of the many-body system, and this is defined as this quantity here. So I will define what I mean by all this notation here. So alpha and beta refers to the spin or some other quantum indices. Here it represents the spins, and this T, this notation capital T, refers to time ordered, which I will define later. It is a time-ordered operator which order the 2 times t and t prime in a proper order, time order. So we need the proper time order in order to have a really consistent definition of the Green's function. Okay? And because of this advanced and retarded type of Green's function, we need to really follow which comes earlier and which comes later. As a result, we need the time ordered. We need to time order those particles. And this notation, expression value with 0 in subscript refers to the ground state expectation value. So everything follows quantum mechanics. It's just that at t equals 0, there's no partition function yet, and everything just generalization of a single particle quantum mechanics. We just have an extra notation which time orders those particle states, and this single particle Green's function has the precise interpretation that the other questions that raised earlier, that you create a particle at x prime and t prime, and then you destroy that, or vice versa. But here it is the other way around, that you first create a particle, single particle, because this is the dagger, refers to the creation of a single particle state. You create a single particle state with a spin beta at x prime t prime, and then later or earlier, whatever, and you destroy that particle. But it's not that particle, because now the spin indices could be different. You destroy a particle labeled by the spin indices alpha. You create a particle labeled by a spin beta. So you may not destroy and create the same particle. You may create particle 1, but destroy a particle 2. But whatever you create or destroyed, what you do is to create something and destroy another thing. And you take the ground state 0 temperature expectation value of such processes, and you time order these 2 operators. You put a minus I here, and that's the definition of the single particle Green's function out of a many-body state. Right? Is that clear? 100% sure, no confusion. So this is very clear-cut definition, and in single particle quantum mechanics, you could calculate this thing precisely in a non-interacting single particle system. But in many-body system, this is a really difficult task to exactly compute this thing. The best thing we can do is do perturbation and do some approximation. So that's all. And you could generalize. So let me just define. I haven't finished that definition yet. So this type of time ordered, what is the definition of the time order? What kind of time order? So let me just specify the time order. This is what I mean by time ordered. So what I mean by time order is that if t, this time t, appearing on this destruction operator, is the later time compared to t prime, then I keep this order, side-by-side dagger, with a minus I. It applies to both on the fermions. However, if the time orders between t and t prime are the opposite, meaning if t prime is a later time, but t is an earlier time, then I should switch the order between side-by-side dagger. So I put dagger on the left and put non-dagger on the right, and then I should put this I with the minus plus different signs, and the minus refers to boson, and the plus refers to fermion. Meaning for both of the fermions, the single particle Green's function are defined in a very similar manner, except you have a plus-minus sign difference. The reason why you have different signs is because precisely this statistics, right? The fermion satisfy this anti-commutation rules, but the bosons satisfy the commutation rules. So because they're different quantum statistics, and to be consistent with their quantum statistics, we should put a minus here and plus there, respectively. So you may want to ask, why do I need to define my time-ordered operation like this? Why not the other way around? Of course, you could do the other way around, whatever way you like, but you need to be consistent all the way. And this is the convention that most of the experts and textbooks use, so we just follow this convention. Of course, you could define the time order in opposite fashion, but then it's really difficult to really do bookkeeping, all this notation and signs with all this well-known references. So there's more than one way, okay, to define your time ordered, but we follow this convention. Is that clear? So let's take a short break. When we come back, we will generalize this single particle Green's function to many particle Green's function. So you could simultaneously destroy a group of particles, and then not simultaneously, but you could destroy a many particle states and then create another many particle states at different space and time locations, and then calculate this transition amplitude. And there's a mathematical knowledge that you may need to have in order to better understand this stuff is the complex integration and residue theorem. And this complex analysis is necessary in order to study so-called analytical properties of the Green's functions, especially in momentum and frequency basis. But I believe you have enough knowledge on that stuff. Okay, so it's not difficult. It's just applied math or mathematical physics at the undergraduate level. So let's just generalize this single particle Green's function to m particle Green's function. So like I mentioned, I could consider creation and destruction of a group of particles at many different space and time locations labeled by x1, t1 up to xn, tn. And then I could study how they space and time evolve, and I will time order all these operators. So suppose I consider m particle Green's function, meaning I destroy m particles and I create m particles, or I create m particles, I destroy them. So this definition follows the single particle Green's function. I create n quantum single particle states labeled by those space and time locations, and then at the different time and space locations, I destroy them, and I try to calculate this transition amplitude of such processes. I time ordered all this psi and psi dagger, and I evaluate its ground state abstraction value and put this prefactor minus I to the power of n. And because you get n psis and n psi daggers, and each single particle transition amplitude, you should put the minus I factor. So there are n such a single particle Green's function. Therefore, you get minus I to the power of n in front. So other than that, it's the same definition. So you could calculate and also measure 2 particle Green's functions, 3 particle Green's functions, 4 particle Green's functions, any particle Green's function you like. And many physical observables such as I already mentioned previously, say current correlation functions are 2 particle Green's functions. And spin-spin correlation functions could be also expressed in terms of the 2 particle Green's functions. So many interesting correlation effects could be reduced to 2 particle Green's functions. And 2 particle Green's functions could be further reduced to the product of the single particle Green's function. But formally you could define this. It's really difficult to calculate in practice. So what you really want to do is to really decompose this n particle Green's function in terms of single particle Green's function. So all these correlation functions is a function of G single particle. Okay, it's a complicated functions of single particle Green's function, but you know single particle Green's function very well, and you know this functional form of this reduction, and as a result, you know the answer for this many particle Green's function. And this is a strategy. So we don't know exact way to calculate the n particle Green's function, but we can reduce this to what we do know. And this is the power of a Green's function method, because everything is reduced to single particle level, and you know that. And as a result, you could make progress. Let's just study this time-ordered Green's function, especially those relation between the retarded advance and the full Green's function. That question was raised earlier. So in order to try to relate this retarded advance Green's function to this full Green's function, we need to define another 2 sets of Green's function called the greater and lesser Green's functions. And this definition, the purpose of defining such a Green's function is to confuse you. So that's just a joke, but so there are relations between greater and lesser Green's function, the retarded advanced Green's function, the full Green's function, which will be addressed later. But let's just define this, G greater and G lesser. So one refers to the space and time coordinate x1, t1, and 1 prime refers to x1 prime, t1 prime. and so on and so forth. So the full Green's function between these two space-time coordinates is a function of a g greater and g lesser with a proper theta function in front. And let's just define formally what is the definition of g greater and g lesser. This is g greater and this is g lesser. Okay, so g greater refers to the first component of this expansion or separation here, that T1 is greater than T1 prime. As a result, only the first term survives, the second term vanishes because T1 is greater than T1 prime, and the argument is that the theta function is negative, and theta of a negative number is 0. Remember that. And likewise, g lesser only concerns the time order such that T1 prime is greater than T1. So that the first term vanishes, only the second term survives. Of course, you could define your g greater and lesser in the opposite way, but in any case, there is always a term which involves T1 is greater than T1 prime, another term the opposite time order. So you can always decompose your correlation function, Green's function, in terms of g greater and g lesser. Whatever notation you like to name it is your choice. You can call this g greater, g lesser, and g lesser, g greater, whatever you like. But conventionally, people just define g greater and g lesser this way. So we better follow this convention. And there's a prefactor C here, which is the special factor for boson and fermion particles. And this C is +1 for bosons and -1 for fermions. In other words, there's a +-1 factor in front for boson correlation function. This is plus, and for fermions is minus, for the same reason that boson and fermion satisfy opposite commutation, any commutation rules. As a result, this factor are opposite. All right, so we introduced many definitions today. I apologize for this, but it is a necessary complication because later you'll find that we could very conveniently extract all the information we like based on what we have defined today. G lesser or G greater, G retarded, G advanced, and they have purpose to be defined and to be used. So let's just look at this relation between retarded advanced and G greater and G lesser. So first, the retarded part, as we just defined. So we could prove this later, and this is the relation, correct relation between retarded component Green's function and linear combinations of the G greater and G lesser, like this, with a minus sign between these two terms, and we multiply the theta function afterwards. So you can follow the definition of the G greater and G lesser just written here, and then you could superimpose these operators, psi dagger and psi dagger psi, and you can form either commutator or anti-commutator between psi 1 and psi dagger 1 prime. So let me just refresh your memory. -1, which means that this is -1 for boson and +1 for fermion. So this -1 in the subscript refers to this commutator, but +1 refers to the anti-commutator. And put the minus sign in front of the C refers to that when C is 1 and there's a -1 here, which means that this commutator is for bosons and anti-commutator is for fermion. Remember, it's C +1 boson and -1 for fermion. And this is precisely what we expect because for bosons, you have this commutation relation, right? And as a result, this single particle Green's function is also the function of the commutator. But for fermions, you get anti-commutation relations. As a result, this combination should be anti-commutator. Okay? But you could convince, this is a simple exercise. I don't want to assign you this as homework. It's just you can convince yourself that you plug in this here and you get this. And what about advanced Green's function? Well, advanced Green's function is here. So you get the corresponding advanced component of the Green's function is another linear combinations of a G greater and G lesser in the opposite way. So what is the difference? Well, the difference is whether there's a minus sign here and the time ordered in the theta functions between advanced and retarded components of the Green's function, the opposite. But their definitions are really, really similar. So here comes the very important statement here, which connects to what we really observed in the laboratory. The physical observables, so let me just write here. What we can measure in the laboratory, in the real experiments, are functions of the Green's function. Remember that. But what is the precise mathematical formulation for this observables? Suppose I have an operator in quantum mechanics, for example, the Coulomb interactions or something like this, which I call this O, operator O. Well, this is a single particle interaction. So suppose I have some kind of potential scattering, which could lead to the scattering of a single particle by some kind of a delta potential, for example. And you could actually see such kind of observables in quantum mechanics. And what we want to measure is the expectation value of this O operator. And this expectation value of this operator O is precisely expressed in terms of the Green's function that we defined today. So this is the statement, and this is the correct answer to really observe this operator in quantum mechanics in the lab. And what you really measured is this quantity down the right-hand side, which is the convolutional integral of an interaction strength O in different spatial locations times Green's function, single particle Green's functions. So this is precisely the solution coming from the Schrödinger equation. Remember that, okay? But this is what you really measured in the laboratory, some expression value of some single particle operator or single particle interactions in quantum mechanics, and what you really measured is this convolutional integral. As a result, the key point of this correspondence is to find out what this G is. So I guess time is up, and this is a perfect time to stop today. And let me summarize. We define mathematically and physically what it means when we say there's a Green's function. And it describes this transition amplitude of a quantum mechanical state from one to another space and time locations. And we formally define different types of Green's functions today. And there are some homeworks that you need to do. We will continue with this line. And then we will Fourier transform the single particle Green's functions at t equals 0. And then we will define electron, single particle electron Green's function, and single particle boson Green's functions as well. And then we will move on to the finite temperature Green's functions. Okay, so enjoy your weekend, and I will see you 2 weeks from now.